So, good morning, professors. I'm from United Christian College, and the topic I'll be talking about is on the divisibility of Catalan numbers. And this PowerPoint is divided into 5 sessions. Firstly, we define C0 is 1, and Cn is this recursion relation. And Cn can also be represented by this explicit formula. Particularly, we'll have this formula holds for every positive integer n. Secondly, for an integer n is greater than or equal to 2, we let Vpn, called the periodic valuation of n, be the highest power of p dividing n. So here's a well-known theorem that this class of Catalan number is indivisible by 2 for some integer k. In 1971, Alter and Kubuta generalized it to theorem A, which is this class of Catalan number is indivisible by p for all of prime p. Then they further proved this theorem B as follows, and they proved that Cn-1 will be this sum involving this inequality of Ni. But, however, it seems that this symbol Ni and epsilon I are constructed artificially, so someone may ask whether there exists any natural and explicit formula for theorem to find VPCn. Besides, it seems that there is a bug in theorem B. Owing to it, in 2006, Deutsch and Sagan, they answered this question partially, and they show a natural way to find V2Cn by using this formula. So you may ask what is a natural way is. So in this example, we expand 63 in base 3 expansion, and we notice that R0 equals to R1 equals to 0, but R2 is not. So we can naturally deduce that V3 63 equals to 2, and similarly, we can also apply this natural way to find VPCn by considering the digits of Cn in base pair expansion. However, it's not achievable as Cn usually has thousands of digits, like C25,000. It has more than 10,000 digits. Fortunately, in this paper, we found the connection between VPCn and the digits of n in base P expansion. As n has only a few of digits, it's become possible for us to derive VPCn naturally by considering the digits. So here's our main result. In theorem 2.1, we let m and p and the digits follow these rules. For every positive integer I, we set epsilon I be 1 if Ni satisfies this inequality. Otherwise, epsilon I is 0. Then the VPCn is this sum minus the capital NP, which is the frequency of carries when 1 is added to n in base p. The next part is the theorem 2.2, and we classify all the digits into S1p, S2p, and S3p. And these digits, Ri must belong to one and only one subset, and the 3 subsets are disjoint. Then we decompose S2p into disjoint subsets by classifying all the consecutive digits into new subsets Tp. Then S2p equals T1p union T2p to TKP for some positive integer k. So here's the structure of the digits, and you can see that all the digits are classified into in neither S1p, S3p, or TP. And you may notice that each subset, TP, T1p, T2p to TKP, lies between S1p or S3p. So in theorem 2.3, we define a new set, BP. The number Ri1 minus 1, Ri2 minus 1 to Rik minus 1 are the digits right before those sets TP. Thus, BP consists of the digits right before those sets TP and belongs to S1p in the meantime. Then we'll have this formula for VPCn. But how about this summation? This sum means that if Riq minus 1 belongs to BP, or you may say if it belongs to S1p, then the cardinality of TQP will be contributed to VPCn. So you may see this picture in this example. Since Rik minus 1 lies right before the set TKP, so the cardinality, and this number belongs to S1p, so the cardinality of the following set TKP will be added to VPCn. So before starting the proof, I'll introduce the three necessary lemmas. By using lemma 3.1, we can derive 3pn factorial. And in lemma 3.2, we'll have a formula for the floor of x. For lemma 3.3, it shows that Vpn plus 1 equals to capital NP, which is the frequencies of carries when 1 is added to n in base P. Our next step is to prove theorem 2.1 by applying lemma 3.1 and 3.2. It shows this formula for VPCN. Then we decompose this sum into two parts. Since p is greater than or equal to 3, if k is also greater than or equal to n plus 2, we can show that n over p to the power of k plus 1 over 2 is smaller than 1. So the second sum in blue color is equals to 0. Here's how we solve the first sum. By expanding the sum, which is in red color, we can show that it equals to a fraction plus a summation, where this fraction is equals to Vpn factorial, and epsilon I is what we have just defined in main result. In the proof of theorem 2.2, we'll evaluate this sum. If Ri belongs to S1p, then Ni will satisfy this inequality, and thus epsilon I will be 1. If Ri belongs to S3p, then Ni will not satisfy this inequality, and thus epsilon I will be 0. Owing to it, we can know that every digit in S1p contributes 1 to VPCN, but the digits of S3p do not. Our next step is to tackle the digits in S2p. If RIQ minus 1 belongs to S1p, then we can know that epsilon IQ minus 1 equals to 1 for J, which are the digits in TQP. And we can show that epsilon J equals to 1 for all the digits in TQP if RIQ minus 1 belongs to S1p. Similarly, we can replace S1p by S3p, and it shows that epsilon J equals 0 if RIQ minus 1 belongs to S3p. Owing to it, we can know that if the digits right before a set TQP belongs to S1p, then it contributes totally the cardinality of TQP to VPCN, but it do nothing if the digits belongs to S3p. By applying this new formula, we can show that theorem A is a special case of theorem 2, and we also have this class of Catalan number is indivisible by k. For corollary 6.1, we can know that the highest power of p dividing this class of Catalan number is 0 by applying theorem 2.2. In corollary 6.2, we know that the cardinality of S1p equals k, and BP is an empty set. So we let J equals this number, and we can deduce this formula 4.1. Here we need to consider two cases. In case 1, we consider P is equals to 3. We'll have the highest power of 3 dividing this class of Catalan number is 0. In case 2, we consider P is greater than or equal to 5. And if I is equals to 1, we'll have the highest power of P dividing this class of Catalan number is 0. For I satisfy this inequality, we'll have the highest power of P dividing this class of Catalan number is 0. So the proof of corollary 6.2 is finished. So here's an example to find V3 C1186. First, we expand C1186 in base 3 expansion, and then we classify the digits into subsets S13, S23, S33, and T3. Since the cardinality of S13 is 3, then the digits lying before T2P belongs to S13, and capital N3 equals to 1. So we have the highest power of 3 dividing C1186 equals 2. Similarly, we can expand it in base 5 expansion and classify all the digits again. So we can note that V5 C1186 equals to 3. Particularly, we want to consider C25016, but obviously it cannot be computed by the website. However, our formula can still be applied on it. We expand 25016, and we classify the digits again. By observing the digits, we can again derive the value of V3C5016, which is 5. So here's the conclusion. We give a complete characteristic of the VPCN for an odd prime P, which is this formula. And this formula is natural and more convenient and more easier to apply. Besides, this new formula can also help overcome some existing limitation. As you notice that the website cannot compute the catalog number with any for any greater than or equal to 25000. However, we can think about writing an efficient algorithm by some computer language. So it's something like that we talk about, and it can be achieved by some technology. So, and this is an extra problem, yes. This is the end of my presentation. Thank you.
Okay.